Excellent. Eric, you can please start.
Okay. Thank you all for coming to my defense. Today, I'm going to talk about magnet superconductor hybrid systems. And these are a promising new platform for the engineering of topological superconductivity. And to introduce topological superconductivity, I first want to talk about what is topology. So topology is a branch of mathematics. It studies how things stay invariant under some deformation. And historically, one of the first times topology came up was in the problem of the 7 bridges of KÖNIGSBERG. And so here we have a map of the town and we have 7 bridges. The problem was, can you go on a walk that crosses all of these bridges, but you can only cross each bridge exactly 1 time? So Euler, he wanted to answer this problem, and very characteristic of Euler, in doing so, he invents a whole new branch of mathematics called graph theory. So what he did was he abstracted this map into a graph, which will look like this. So the land turns into these vertices and the bridges connect these vertices as edges. And so what he noticed is that if you're going on a walk, for instance, in the center island, you would have to go in and then out, and then in and then out. And so these, when you're going through the island, these bridges comes in pairs, but if you have an odd number, then you come in, but nowhere to go out. And so this means that if you have an odd number of bridges and a vertex, then it has to either be a starting point or an end point. So here we have all vertices being odd. And that means that you can't go on a walk in KÖNIGSBERG that crosses each bridge exactly 1 time. And this was kind of an early sign of topology because you can imagine deforming the land. The shape of the land doesn't matter. The graph would stay the same. The only way the answer to that problem would change is if you add new bridges or destroy some bridges, which unfortunately happened in World War II. And now it's the 5 bridges of KÖNIGSBERG. And indeed, you can go on a walk that crosses each bridge once. Euler continued with this and made something called the Euler characteristic chi, which is the number of vertices minus the edges plus the faces. So if we count the number of vertices and then the edges and the faces, which are the areas between these edges, including the outside one, if we count them and calculate this number, we get the number 2. And this number 2 is actually always the number 2 for any graph that you can draw on a piece of paper like this without these edges intersecting. We can also look at the Euler characteristic for different shapes. Here's a table of different convex polyhedra and a list of their number of vertices, edges, and faces. And the Euler characteristic of all these shapes are also 2. What about something more smooth, like a sphere? How will we calculate the Euler characteristic for that? Well, here I drew it as a wireframe, and you could imagine you could count the vertices, edges, and faces and take maybe some sort of limit. But there's a theorem called the Gauss-Bonnet theorem, where you can actually calculate the Euler characteristic as this integral over the manifold of the Riemannian curvature. And this is a topological invariant. As you stretch or deform the sphere, the curvature locally would change, but the total curvature remains invariant. What about this object here? This is called a torus. And so on the outside, the Riemannian curvature is actually positive. And then the inside, we have negative curvature. So if we integrate all of that curvature, what happens is that it all cancels out, and the Euler characteristic is 0. The Euler characteristic is actually connected to the number of holes. It's 2 minus 2 times the genus, where genus is the number of holes. And these are both topological invariants. And so the sphere has Euler Euler characteristic of 2, the torus has 0. So these are topologically distinct objects. There's no way to deform one into the other. The only way to do that is if you were to either rip the surface or stitch it together somewhere. This actually has a direct application to materials. Materials can be characterized by different topological invariants, and when the topology of these systems actually manifest themselves in experimental signatures. One that I will talk about today is the Chern number. The Chern number is also an integral over the Brillouin zone manifold of the Berry curvature. So this is very, very similar to the Euler characteristic. And this Berry curvature is defined as these derivatives of the wave function. So what the Berry curvature would look like, here I have 2 electronic bands, and the color is showing the curvature. So here it's a little blue, so it's a little negative, and here it's a little red, it's a little positive. And we can deform these bands, but the total curvature remains the same, unless they touch. And then the curvature can kind of transfer over, and now we have a total curvature of -1 on this bottom band. So this is a topological band, and in a physical system, bands are filled up to the Fermi energy. So if the Fermi energy is inside of this energy gap, then the system is in a topological phase. And that topological phase is protected by the energy gap of the system, because the only way to change the Chern number of the system would be to close that energy gap and transfer some of that curvature over. There's a whole table of different topological invariants for gap systems, so insulators and superconductors, and the Chern number is just one of them. And so here, in this part of the table are a lot of the superconductors, and the Chern number is in this 2 dimensions. So for 2D topological superconductors, the topological invariant is the Chern number. And what's interesting about these systems is that at the edge, you get what's called a chiral Majorana edge mode. So this chiral Majorana edge mode is a 0 energy state, and you get this because at the boundary you have a topological side, and then you have a trivial vacuum. So at the interface, you have to have a phase transition, which means that you have to close the energy gap. And so you get a 0 energy state. And there's something called the bulk boundary correspondence that says that the number of these edge channels is equal to the difference in these Chern numbers. And we can also find very low, we can have superconducting vortices in a 2D topological superconductor, where you have a single quantum of magnetic flux go through. And in the core of the superconducting vortex, you get what's called a Majorana bound state. And so that is also a 0 energy state that you find in these 2D topological superconductors. And you can also have 1D topological superconductors, where you also get Majorana bound states at the end of the wire. These Majorana 0 modes are highly sought after because they have very exotic exchange statistics. So regular particles, such as bosons, when you exchange 2 bosons, the wave function is symmetric. So exchanging 2 identical particles doesn't change the wave function. But for fermions, the wave function is antisymmetric. If you exchange 2 fermions, you get a minus sign. And that gives rise to things like the Pauli exclusion principle. Anyons can be anything in between. For instance, you could have a phase between 1 and -1. This is a abelian enyon because you get a phase, but there's also non-abelian enyons, where an exchange between 2 non-abelian enyons is represented by an operator, usually called a braid. You're braiding the 2 particles. And these braids don't commute with other braids. And so it's non-abelian. non-abelian anyons are, people have been looking for these because you can use them for topological quantum computation. This is a different way to do quantum computing, and it's an inherently robust way to do quantum computing because you can encode quantum bits of information in pairs of Majorana zero modes. And since it's encoded in spatially separated Majoranas, a local perturbation wouldn't be able to break that information. And so it's inherently robust against local perturbations. And you can also create robust quantum logic gates. For instance, the Hadamard gate, you can design using 3 different braids. And braids are also robust because if you were to look at the world lines of these Majoranas, they create these strings and they create these knots in space-time, and you can't unknot these braids with any sort of perturbation. These are topologically distinct, and so you create topologically robust quantum logic gates. There's been many different ways to try and realize these Majorana zero modes. One example is using semiconducting nanowires and then encasing that in a superconductor. Another is to use Josephson junctions and putting that on the surface of a semiconducting thin film. And what I'll be talking about today are these magnet-superconductor hybrid systems, where you have a superconducting substrate and magnetic atoms on the surface. And there's also 2D realizations. Here we have magnetic cobalt atoms and superconducting lead. And also this example where we have iron monolayer grown on top of the surface of rhenium. And this example I will talk about later in my defense. So to use topological superconductors and devices to make useful topological devices, we need to know the answers to questions like, how can we engineer these topological phases? And more importantly, can we tune between these different topological phases? Also, we need to be able to identify Majorana modes and distinguish them from trivial states. Because you could have a state that's at 0 energy, but it turns out that it's trivial and you can't use it since they don't have the non-abelian exchange statistics. And lastly, how can we manipulate Majorana modes and how robust are they? Because if we're going to design devices, we need to be able to manipulate them, and we need them to be robust so that we can use them usefully. So here I'll introduce the theory of the magnet superconductor hybrid system. The Hamiltonian has 3 key ingredients. We have S-wave superconductor. The substrate is S-wave superconductor. And on the surface, you break inversion symmetry. And so when you have broken inversion symmetry and spin-orbit interaction, that creates what's called the Rashba effect. So we add a Rashba spin-orbit interaction. And then we have these magnetic atoms on the surface. And the local magnetic moment interacts with the spin of the electrons in the substrate.
Quick question. Is a superconductor extended? Is it bigger than that island?
Yes, so this is a 100 nanometer image, but the superconductor goes out for for very large.
Okay.
So the first term of the Hamiltonian is this simple type binding model, which gives us a band. And then we add superconductivity, which will gap the band at the Fermi energy. Then we add a Rashba spin-orbit interaction, which couples the spin to the momentum. And so what happens to the dispersion is that we lift the spin degeneracy by splitting the bands sideways, like so. And then lastly, for the magnetic interaction, these magnetic atoms act as a local magnetic field, like a Zeeman term, which splits the bands up and down, like so. Okay, so we can take the thermodynamic limit and calculate the topological invariant. And for different parameters for the magnetic exchange and the chemical potential, we get these different topological phases. Here it's -1, 1, and 2. And if we flip the sign of the magnetic interaction, then we flip the sign of the Chern number to 1, -1, -2. And we want to study the boundary states, these zero energy Majorana modes. So we put this in a ribbon geometry, and we make it finite in the x direction, but infinite in the y direction. And so on the boundary, we should get these chiral Majorana edge modes. And so to see if we have a state at zero energy, we look at the local density of states. And so in the bulk of the system, in the middle of this ribbon, we don't see states inside of the gap. And then we see the superconducting gap up here. And then at the edges of the ribbon, we see a state at zero energy, and it also goes all the way up to the superconducting gap. And since this is a translationally invariant system, we can look at the dispersion of this. So here we have the bulk superconducting gap, and then this is the edge dispersion. And this is a topological edge dispersion because it connects this bottom bulk to the top that crosses the superconducting gap. And if we again look at the local density of states, the center of the ribbon has this superconducting gap, but in the along the edge, what we get is this flat density of states. And that comes from the shape of this dispersion. It's relatively linear, and so we get a relatively flat density of states. So what happens in a phase transition? So we can change the chemical potential to go to different topological phases. And so as I change the chemical potential, eventually we close the bulk energy gap, and we still have these edge bands, but these are trivial. They do not cross the superconducting gap. And if we keep on going, we again close the superconducting bulk energy gap, and now we have two edge bands. And this comes from, again, the bulk boundary correspondence, where the Chern number is 2, so we have two edge bands now.
Eric,
Yep.
Excuse me, can you remind me what is being changed?
Chemical potential. So,
potential.
Yep, here, what that animation was going from here to here.
Mm-hmm.
Okay, so what will we expect to see in an experiment? One useful feature about these magnet superconductor hybrid systems is that we can use scanning probe techniques to look at local features on the surface of the system. And we're interested in the local density of states to find the zero energy Majorana modes. And to do that, we can use a scanning tunneling spectroscopy experiment, where we bring a very sharp tip very close to the surface of the system, and then we can apply a voltage between the two. And then what can happen is the electrons will tunnel into the system, and then we can measure that current. And so here's the density of states of the tip and the system. The tip we want to have relatively featureless, and as we increase the voltage, we fill more states in the tip, and those states can tunnel into the system, which we can measure through the current. And so as we look at how the current changes, as the voltage changes, we can get the shape of the local density of states. And so what should we see in a trivial island of magnetic add atoms? What we should see is just a superconducting gap and no Majorana edge state. So here we see just the superconducting gap, but if we go into a topological phase and measure the LDOS at the edge of this island, then what we expect are these edge states near zero, very, very close to zero energy, and they're pretty evenly spaced inside the superconducting gap. And that comes from having a very close to linear dispersion on the edge of the island.
Sorry, how do you make sure that the magnetic island doesn't destroy superconductivity?
Yes, so if you, so the way that, if we were to not have spin orbit coupling, the magnetic exchange in this system is strong enough to destroy that superconductivity. But by having a Rashba spin orbit interaction, what we're doing is having, we're gapping, so usually have pairing between a singlet pairing, but with the spin orbit interaction, we're able to have a P-wave-like gap that that is, yeah. And so it's because we have spin orbit interaction that we have a gap even though we have magnetism.
Okay.
And experimentally, right, they actually, when they build these systems, they see that the gap is reduced, but it's still there.
Yeah, it definitely is suppressed from the magnetism.
Yeah, but as Eric said, one of the interesting results that we found is that the Rashba spin orbit interaction seems to stabilize the gap for much larger values of the exchange coupling than you would expect.
Eric?
Yep.
How do these peaks on the bottom plot, the red peaks, correspond to the what I see on the left plot?
So this is a finite size island, and if we were to have discrete K points, these would be evenly spaced in K, and so you would have evenly spaced in energy.
Would the picture on the left change?
So the picture on the left is for a ribbon. In this case, we have a circular island. And so instead of Ky, we would have angular momentum.
Yeah, but I mean, if you replace momentum by angular momentum, you would still see one chiral edge mode crossing. So the picture would be similar, but given that the radius is small, it would, as Eric said, just like maybe 6-7 points on that red line instead of a continuous line. But the picture would hold.
The picture on the left?
Yeah.
Mm-hmm. But I still do not, will the picture on the right still have peaks?
Yeah, so these are discrete states. So if the way that we calculate the local density of states is the imaginary part of the Green's function. If we were to take that infinitesimal imaginary part to 0, then these would be delta functions.
Mm-hmm. But what determines that? So what I'm trying to understand is, can I look at the picture on the left and determine where those peaks will be? Or this information is not?
For instance, let's say that I were to do it in this system.
Mm-hmm.
And I set the system size to be small, then I know exactly the Ks. For instance, let's say that I only have 10 sites in the Y direction, then I would have 10 K points here. Then I know which ones those would align to.
Mm-hmm.
And that would be a peak in this density of states.
Excellent. Thank you.
Yeah.
Thank you.
Okay. And if we look at spatially at zero energy, what we have is our Majorana zero mode, and it's localized to the edge of our magnetic island. Furthermore, we can calculate the conductance. This is di dv, what would be measured in an experiment. And we find that the conductance is quantized, and it's proportional to the absolute value of the Chern number. So for C equals 1, we have this one edge band, but for C equals 2, we have 2 of these, and so we have double the conductance. And it shouldn't matter, this is a topological superconductor, it shouldn't matter the shape of the island. So we looked at a deformed magnetic island, and we also see that we get a Majorana zero mode localized at the edge. The LDOS has states that go across the superconducting gap, and the conductance is quantized. Another feature that we found is that you get persistent supercurrents. So you have this magnetic island that breaks time reversal symmetry, but on the substrate, you do have time reversal symmetry. And so at this interface, you get these persistent supercurrents that go around the island. And a unique feature of these supercurrents is that the direction, this one's going clockwise, reflects the sign of the Chern number. So the Chern number is negative here, but for a positive Chern number, we get a counterclockwise supercurrent. And so these supercurrents carry charge, and so the moving charges would induce a magnetic field. So if you have a very fine magnetic field sensor, such as a scanning squid or a superconducting quantum interference device that can measure very, very small magnetic fields locally, you would be able to find the direction of these supercurrents and be able to pull out the sign of the Chern number. So that's a theory. Do we actually see this in an experiment? We collaborated with a group at the University of Hamburg who grew these iron monolayer systems on the surface of rhenium, which is an S-wave superconductor. And so here's a topographic image of that iron monolayer on rhenium. And there, in this sample, there is an oxide layer that's a single atom thick. And they measure the local density of states using scanning tunneling spectroscopy. And they see this zero energy state localized to the edge of the island. And so we developed a model for this system for the d orbitals and took a 1-to-1 scale of all the atoms from this topographic image and put it in a real space system and calculated the local density of states. And what we got was very similar, a zero energy state that was localized to the edge of this magnetic island. And we know that this is a topological edge because we can, with this model, we can calculate the topological invariant. And we get a non-trivial Chern number. We got a Chern number of 20. So we know that this edge mode is a topological edge. And if it's a topological edge, we should see it cross the superconducting gap. So as we go up in energy in both theory and experiment, we see this edge mode. And as we go higher in energy, this localization length starts getting longer until we start getting close to the superconducting coherence peak, after which we only have bulk states. And so now all we see are bulk states inside of the island once we get to the superconducting gap. And an important check is to see if this holds for other samples for different islands. One interesting sample was this iron monolayer, which did not have the interface oxide layer. And in this case, what happens is that because the oxygen atoms aren't in between the rhenium, instead the iron atoms fall in between. And so when we take our model and move the iron atoms in between the rhenium atoms, what we found is that we close the energy gap and we get a trivial topological phase. And so when we calculate the local density of states, since we close the energy gap, all we see are bulk states inside the island for both theory and experiment for all energies. Okay, to use these topological superconductors and devices, we want to make sure that these will be strong, robust against disorder. And so we looked at the stability of the topological phase in these topological superconductors. So here we look at random disorder. And we have these phase diagram where we have these topological phases. And as we increase the strength of the disorder, we see that these topological phases persist up to very large disorder strengths, which are many times larger than the superconducting gap size. And what's especially interesting is if we look over here towards the left of the phase diagram, here we have at the beginning where there's no disorder, it's in a trivial phase. But as we increase the disorder, we go into a topological phase. And so we can get order from disorder. And this wasn't the only type of disorder we looked at. That was the potential disorder. But we also looked at magnetic disorder, random spin orientations, and random percolation type disorder. And in all of these cases, we found very robust topological phases. Next, to use these the zero energy excitations that come from topological superconductors, we want to utilize these and use them in devices. And so we need to know how to manipulate these Majorana zero modes. And we found that you can actually use this manipulation to count the topological invariant inside the system. So one question that remains in these Majorana devices is that what is best for braiding is not yet known. Do we want 2D Majorana zero modes or 1D? And that kind of raises the question, can we go from a 2D Majorana zero mode to a 1D Majorana zero mode? And from the negative space, you might be able to tell, yes, we probably can. So here we're adding single magnetic add atoms. And you can do this with atomic manipulation techniques where you can drag and drop single iron atoms to the island. And by attaching this chain, we're pulling out a Majorana bound state. And this chiral Majorana edge mode is here. And if we shrink that island, it turns into a Majorana bound state. And we can look at the energy spectrum as we go through this transition between two-dimensional and one-dimensional Majorana bound state or zero modes. And we see we have our edge mode, which is like evenly spaced energies. And once we start shrinking the island, the edge band gaps out and the zero mode remains. And so what one particular feature of this is that there is no bulk energy gap closing. So since we don't close the energy gap, that means that we don't have a phase transition while we do this, going between the two different Majorana zero modes. So what happens if we add an additional chain? Now we lost any signature of the edge mode inside the island. And all that remains is the Majorana bound state. And that was with two chains. But in the C=2 phase, we do have some signature where the chain connects to the island. And so if we continue adding chains, eventually we pull out any signature from the edge of the island. And this time it was for 4 chains. And we can actually use this to count the Chern number. So the number of changes, twice the number of the Chern number, and that comes again from the bulk boundary correspondence, where in the C equals -1 phase, you have one zero energy Majorana edge mode. And so by pulling two Majorana bound states, you pull that state out of the island. But for C equals 2, you need to do 2 of those. And so you need 4 chains. This still works for C equals 3. And so here in C equals 3, we still have our edge state and a Majorana bound state at the end of a chain. And as we continue add chains to our island, we start losing signature inside the island. But once we have 6 chains, which is 2 times the Chern number, we lose all signature inside of the island. We can actually create networks with these chains. So we can imagine connecting the ends of these chains. What happens is that the Majorana that was here comes back and goes back into the edge. And so these Majorana bound states went back inside the edge of this island. But we can look at different kinds of networks. And in this case, we do get a Majorana bound state, because here, very similar to the bridges of KÖNIGSBERG, we can go in and out, but there's an odd number of edges here, so it has to be a terminal point. And so you end up with a Majorana bound state. And here, where all the vertices are odd, we get a Majorana bound state at each vertex. Yeah, so far I focused on ferromagnetic ordering. So one of the problems that come from these systems is that it's very hard to change the topological phase, because the phase diagram that I showed, we have the magnetic exchange interaction and the chemical potential. And these are material properties that are difficult to tune. So instead, can we use magnetic structure as a tuning parameter to be able to go between phases? And additionally, it requires spin-orbit interaction. And so that limits the different superconductors that we can look at. So instead of having spin-orbit interaction in the superconductor, can we move it into the magnetic structure and still get topological phases? So we look at Skyrmion lattices. So this is an interesting kind of magnetic ordering where you have a lattice of skyrmions. A skyrmion has these magnetic moments that rotate from the center outwards. And although there isn't a Rashba spin-orbit interaction in the superconducting substrate, what we can imagine doing is rotating each of these spins into a ferromagnetic ordering. But each site would rotate differently. And so the hopping between them would rotate as well. So if we look at how that hopping changes, we can induce a effective Rashba spin-orbit interaction. And so we can calculate that. And what we get is at the center of the skyrmions, we get this very strong effect, induced Rashba effect. But in the corners in between the skyrmions, a very weak effect, which you can look here locally, it looks ferromagnetic. And so we don't have a induced Rashba effect there. But with this, we have superconductivity, we have a Rashba effect, and we have magnetic ordering. So we have the 3 ingredients that we need for topological superconductivity. So we calculated the phase diagram for this. Again, we have our magnetic exchange and the chemical potential. But as we change the size of that lattice, the sizes of the individual skyrmions make them bigger and bigger, what we see is that the phase diagram shifts over to the left. And if we look at a specific cut, we can look at how the critical line shifts, and this goes as 1 over r squared. So normally when you're fabricating these materials, growing them, you are pretty much throwing a dart randomly onto this phase diagram and hoping that it lands in a topological region. But now with the size of the skyrmion, what we can do is shift that topological region to that dart. And this can actually be done in an experiment because the size of the skyrmion can be controlled by an external magnetic field. So that gives us a tuning parameter that allows us to go between different topological phases. And this is one type of skyrmion. There are other types of skyrmions. You can rotate these spins, and these are all different kinds of skyrmions. It turns out that there's a gauge transformation that connects all of these different skyrmions, and that leaves the Hamiltonian invariant. And so this phase diagram applies to all of these different types of skyrmions. And now we want to study the signature of the Majorana zero modes. So we look at a ribbon geometry again. We put this magnetic ribbon on top of a superconducting substrate, and we have these skyrmions. And if we look at the local density of states, we get at zero energy this edge state. But if you notice, it's only focused on the corners of the skyrmion. So the edge mode is, it kind of rotates around these skyrmions. And this signature would be an electronic signature in the scanning tunneling spectroscopy, but it also shows a signature of the magnetic structure. And next we calculate the supercurrent. What's interesting is that around the rotating spins, around each skyrmion, you get these persistent supercurrents that orbit around the skyrmions. And so for each skyrmion, you get net zero current because it's just orbiting in a circle. But at the edge, at this edge, you get a remaining supercurrent that is chiral around the edge of the ribbon. Okay. For the last part of my talk, I want to talk about the origin of topological surface superconductivity in FESETE. It's a iron-based superconductor, which has gained a lot of interest recently. Here's the crystal structure. So what we have is a layered structure, and these iron atoms form this square lattice. And in between, you get these alternating up and down selenium or tellurium atoms. And it has this kind of phase diagram for different doping. In the iron tellurium side, we get a spin density wave. And as we go to the iron selenide side, we get a superconductor, which has a TC of around 10 Kelvin. And the superconductor is interesting. It has an S plus minus wave symmetry. So here's this Fermi surface in the normal state. And in the center, we have these two Fermi surfaces. And the order parameter here is positive, the superconducting order parameter. And then on these edge Fermi surfaces, the superconducting order parameter is negative. So it's a S plus minus wave symmetry. And what's nice about this material is that the coherence peak, the superconducting gap of this material is very large. It's between 1 and 2 MeV. And it has these three signature, so there's 3 different features in this, which comes from the 3 Fermi surfaces. So this 1 to 2 MeV superconducting gap is much larger, for instance, in the iron rhenium system, which only had a gap of around 0.3 MeV. So this is a very interesting material, especially around here in the middle of this phase diagram. There's experimental signatures of Majorana bound state or zero energy states and topological superconductivity on the surface. So these experiments, they found zero energy states in the cores of vortices, which is a signature that you would expect from a Majorana bound state. Here, there's a line defect in the surface of FESCTE. And at the ends of the chain, they find zero energy states. And in this experiment at a domain wall, they see an edge state that crosses the superconducting gap, which you would expect from a chiral Majorana edge mode. And to explain this origin of superconductivity, we can imagine that we already have the S-wave superconductivity, and we have a surface, and so we have a Rashba spin-orbit interaction. What's missing is a magnetic order. But recently, there has been evidence from ARPAS experiments that there is a ferromagnetic ordering on the surface of FESCTE. So now we have those three ingredients that we need for topological superconductivity. And so we took a model for FESCTE, and we added those surface effects with the Rashba effect and the magnetic magnetic ordering on the surface. And indeed, we find topological phases for this material. And if we go into a topological phase, we compare it to the experiment with the vortices. Here we added a magnetic field and self-consistently calculate a superconducting vortex. And we can measure, or we can calculate then the density of states, the local density of states inside that vortex. And in the core, we have a zero energy state. And then we also have these other states. These are trivial vortex bound states that are non-zero energy. However, if you look at a topologically trivial case, we don't see a zero energy state. We see states that are split from zero. For the next experiment, the line defects, we added a line of scattering potentials to our system. And for different scattering strengths, we found areas where you would get Majorana bound states at the end of the chain. Here we have our zero energy states. And so if we look at this zero energy state spatially, we see that indeed it's a bound state at the end of the line defect. And lastly, to compare to the domain wall, we looked at two different types of domain walls. So we look at spin domain walls, where we flip the ferromagnetic ordering on the surface. And in this case, when you flip the spin, then you flip the Chern number. And so in the C equals -1 phase, the difference in the Chern number is 2. So we expect from the bulk boundary correspondence 2 topological edge modes, which we see these two cross the superconducting gap. And we also see these trivial edge modes, but these are gapped in the very center, very, very small gap, and those are trivial edge modes. And then we also looked at a pi phase domain wall, where the superconducting order parameter changes sign at a domain wall. And in this case, the Chern number doesn't change, and so we don't expect any boundary modes from the bulk boundary correspondence. And indeed, in the dispersion, it's hard to tell, but these are all not traversing the superconducting gap. And we can look at the density of states of this. And at the domain wall, what we get at zero energy is a state that crosses the gap. And spatially at zero energy, the local density of states looks like this. But if you look between these two different domain walls, they look very similar. So the local density of states is not a marker that we can use to tell the difference between this topological edge state and this trivial edge state. However, we can use the sign of the Chern number, which is reflected in the supercurrent, the direction of the supercurrent. And on both sides of this domain wall, for a spin domain wall, the supercurrents are facing the same direction. But in the pi phase domain wall, what you get is a supercurrent that is in opposite directions, and the net supercurrent cancels out. So the supercurrent is an additional signature which would be able to discern between a topological edge or domain and a trivial domain state. So in conclusion, these magnet superconductor hybrid systems are a promising candidate for the engineering of topological superconductivity. And these systems are very strong. They're robust against disorder. And we can use these systems to manipulate Majorana zero modes and use it to count the Chern number by attaching chains. And we can tune between different topological phases using Skyrmion lattices. And lastly, FESCTE is an intrinsic magnet superconductor hybrid system. And this explains the emergence of topological surface superconductivity. Thank you.
Thank you, Eric, for this very nice presentation, and which is now open for questions. Let me actually stop the recording.